What's up, student geniuses? Miss Sorensen here with proving trig identities. This is by far the hardest topic. You might find it reasonable, but in general, students really have a hard time with this. Please be patient with these problems. Sometimes they take people 10 minutes to do one. You kind of redo it and try different things. These are not problems that are intended to be solved immediately. You might get lucky and guess the right thing right away, but that's not how these problems work all the time. So let's get started with some pre-knowledge. I want to talk about how we can manipulate and identify various trig identities written in a different way. So let's start first with the sine squared theta plus cosine squared theta equals 1. If I want, I can go ahead and subtract cosine squared theta from both sides. So if I subtract cosine squared theta from both sides, the cosine squared thetas cancel, and I'm left with sine squared theta is equal to 1 minus cosine squared theta. So that's one possible way to rewrite a Pythagorean identity. Let's start again. Let's go back to sine squared theta plus cosine squared theta equals 1. I can subtract sine squared theta this time. And this is going to give me cosine squared theta equals 1 minus sine squared theta. So I've already just taken one trig identity and rewritten it a different way. You can do that with all the other trig identities as well. So just be very well aware that when you see possibly a cotangent squared, a cosecant squared, and a 1 in the equation, it could still be this Pythagorean identity, but rewritten in a different way. I'm not going to go through all of them, but yes, all of them can be rewritten to be seen in a different way. What I do want to cover, though, is the following. I want to show you that 9 minus x squared is equal to 3 minus x and 3 plus x. You should be able to identify these as two perfect squares. This is the difference between squares. We've got a 9, which is 3 times 3, and we've got an x squared, which is x times x. And notice how we have no middle term, and those basically get eliminated if I have the same exact expression except one has a minus and one has a plus. If you don't believe me that this is true, you can go ahead and FOIL this out and it will show you that these two expressions are equal. Now you're probably saying, what the heck does this have to do with trig? Well, let's go over to this one right here. If I know that I've got 1 minus cosine squared theta, I can rewrite that as what? As 1 minus cosine x and 1 plus cosine x. And these are both perfect squares as well. 1 is equal to 1 times 1, and we know that cosine x times cosine x does give us cosine squared x. We'll have no middle term because we've got a minus here and a plus here, and those will cancel out the middle terms. Same thing is also true if we were to simplify this one. 1 minus sine squared is going to be 1 minus sine x and 1 plus sine x. And you could FOIL that out just to show that it's true, but it is the difference of squares, and that does work. So those are also the same exact expressions. So what is the process for proving trig identities? Well, first let's look at what a proof is, and then let's go back to this, and that will make more sense. So here's a question you might get. Prove that secant theta sine theta is the same thing as tan theta, that they're equal. So you're proving that that's an identity. What we do is we keep one side exactly the same the whole way down, right? We're going to choose tan theta to keep the same all the way down. But we take this secant theta sine theta and we change it up a little bit. So for example, what is secant equal to? Well, look right here. Secant is 1 over cosine. So instead of writing secant right here, I write 1 over cosine. Now, 1 over cosine times sine, if you want to put sine over 1, you can, and multiply those two fractions. 1 times sine gives me sine, and cosine times 1 gives me cosine. So all I've done in this particular step to get from here to here is multiply those fractions. And then what is sine over cosine? Well, sine over cosine, if we go right here, is the same thing as tangent. Okay, so instead of writing sine over cosine, I can write tan. So I started with this thing right here, and I manipulated it using these rules, and I got tangent theta. Well, I was trying to prove that it was tangent theta, and I just kept rewriting that on the right side every time. And because we have a match, we put check, right? We could even say QED. We have proved that those two things are exactly the same. They are equal. All right, so now that we've kind of gotten that out of the way, we kind of see what a problem looks like. I think it makes more sense now to go back and look at some tips for proving an identity. I highly recommend working with the more complicated side of the equation. Just like we did here, we worked with this. That's the one that we kind of changed around and manipulated, and we got it to look like the easier one. This one says use basic identities to rewrite unlike functions. So for example, instead of writing secant, we wrote it as 1 over cosine. Some other things that they recommend doing is removing parentheses and finding common denominators to add fractions, or even combining fractions and multiplying them. And then simplify complex fractions and reduce fractions to their lowest term. So here's a fraction, and we made that a less complicated fraction by just calling it tangent because of this rule right here. But overall, the general goal is to take a very complicated function like this one, rewrite it so we have a match to have on the other side. Are you ready to try this out for example 2? Okay, here we go. Which one's the more complicated side? Definitely the left side. So I'm going to try to manipulate the left side to get it to look like the right side. So to do that, I think you probably would make the same guess as me, but we're going to just multiply right through. So I'm going to get sine theta cosecant theta, just smushing those together, minus sine theta sine theta equals cosine squared theta. Please notice that I'm not changing this the entire time. I'm just choosing the left one to work with. All right, next thing I'm going to do, and you probably guessed this right as well, is we're going to rewrite cosecant theta. Well, what is cosecant theta? It's 1 over sine. So this is going to be sine theta times 1 over sine theta. And then this is going to give me minus, and well, what is sine times sine? Well, that's sine squared theta. Remember that notation that we've got to know really well. Again, I'm not changing the right side at all. What happens with sine theta times 1 over sine theta? Well, these two things cancel out. It's not gone. We're left with 1 because sine divided by sine is 1. So this is going to give me 1 minus sine squared theta is equal to cosine squared theta. Now remember from kind of the review here is that we can take this thing right here and rewrite it. So if I've got sine squared theta plus cosine squared theta equals 1, I can go ahead and subtract sine squared theta from both sides. And this disappears, and I'm left with a cosine squared theta equals 1 minus sine squared theta. All right, so what am I trying to say over here? I'm trying to say that 1 minus sine squared theta is the same thing as cosine squared theta equal to cosine squared theta. And you might be saying, hey, do I have to actually say that this is because of the Pythagorean identity or manipulating the identity to look like that? The answer is no. If I asked you to write a written proof, you would have to do that, but not in this particular situation. So have we done it? Have we proven this particular identity? The answer is yes. So we put a check mark. Okay, let's try another one. We're going to try to prove that 1 minus sine theta equals cosine squared theta divided by 1 plus sine theta. Which one's more complicated? I would say this one on the right is more complicated. So we're going to work with that one. I'm just going to rewrite this 1 minus sine theta And we're going to work with that one on the right. Well, what is cosine squared theta? Well, we can actually solve for it right here if you want. So I've got sine squared theta plus cosine squared theta equals 1. I'm going to subtract sine squared theta. You might be able to start being able to do this in your head. If you can, I think that's preferred. And that's going to cancel, and I'm left with cosine squared theta equals 1 minus sine squared theta. So I'm going to take this right here and I'm going to replace it because I've got cosine squared theta, and that's the same thing that I have right there. So I'm going to rewrite this numerator as 1 minus sine squared theta divided by 1 plus sine theta. Now you might be able to recognize this right here as a difference of squares. We've kind of reviewed this. So I can rewrite that numerator. Just rewrite that there. Let's rewrite the numerator as 1 minus sine theta times 1 plus sine theta. And if you're confused about why that's true, go back to our review where I showed you how to factor difference of squares. And I still have in the denominator my 1 plus sine theta. Okay. Now, what do you see happening here? If you said you can see something that cancels, you're totally correct. We've got this canceling with that. And so we're really just left with rewriting this side, and we're left with just what we have on the top here, which is 1 minus sine theta, and we have a match. There we go. All right, let's try example 4 here. We've got trying to prove that secant squared theta minus 1 times cosine squared theta equals sine squared theta. Now, you can probably tell that I can do it right the first time, and that's not actually always the case, right? Sometimes I try something and it doesn't work, and it's not that it's wrong, it's just that I've got to try a different method. So when you're doing these on your own, please don't panic and think like, oh, I can't get them as fast as Miss Sorensen. Well, you have to really work at these. Sometimes try something. If it doesn't work, try another thing. All right, let's see what we've got here. Obviously, this left side is way more complicated than the right, so we're going to work with that. And we're going to work with secant squared theta minus 1. And if you look here, we're in pretty good shape. I'm going to rewrite this as tan squared theta plus 1 equals secant squared theta. How can I get a match here? Well, what I can do is just subtract 1. The 1's cancel, and I'm left with tangent squared theta is equal to secant squared theta minus 1. So this right here I can replace, and that's going to be tangent squared theta. All right, times cosine squared theta equals sine squared theta. And again, I'm not changing anything about the right. Okay, now this is when you have to kind of get creative here. If I've got tangent squared theta, how can I rewrite that? Well, notice over here that tangent is sine over cosine. Well, if tan is sine over cosine, then tangent squared is going to be sine squared over cosine squared. I've not explicitly taught you that, but I think it makes a lot of sense. So I've just rewritten that just like that. All right, now we're going to multiply that by cosine squared theta. And that's going to be equal to sine squared theta, hopefully. All right, next thing we do here is we're going to cancel the cosine squareds, because one's in the numerator, one's in the denominator. And that simply leaves us with sine squared theta is equal to sine squared theta. Do we have a match? Yes, we do. Now, I don't know if anyone's like me, but I just absolutely love these problems. I think there's just a ton of fun. Okay, this next problem here, you might notice looks very similar, but actually the right side is different. A little bit different problem here. Okay, here we go. I'm hoping that you see that 1 minus cosine squared theta actually can be manipulated from our first Pythagorean identity. Okay, so if I have sine squared theta plus cosine squared theta equals 1, I can go ahead and subtract cosine squared theta. The cosine squared thetas disappear, and I'm left with sine squared theta equals 1 minus cosine squared theta. Okay, so what does that mean? That means if I have 1 minus cosine squared theta here and here, I can replace it with a sine squared theta. So this is going to give me secant squared theta times sine squared theta is equal to tangent squared theta. Again, not changing the right side. Hopefully you have the right idea here. What do you think we could do next? Well, we're going to rewrite the secant. That's kind of a general thing that if it's written like one of these, we can rewrite it as a sine, cosine, or a tan, but as the reciprocal. That usually helps us cancel things. So this one here is going to be 1 over, again, we're dealing with secant, so it's going to be 1 over cosine. But since it's a secant squared, this also has to be a cosine squared theta. I'm going to write this as sine squared theta equals tangent squared theta. Okay, now you can rewrite this here if you want as over 1 and realize that when we multiply fractions, we multiply across the numerators. So we're going to be left with a sine squared theta over, multiply across the denominators, we get a cosine squared theta equals tangent squared theta. Okay, now I'm going to go ahead and I'm going to look at this value right here, that tangent of theta is sine over cosine. So then sine squared over cosine squared is going to give me a tangent squared theta. And that's exactly what I wanted. Keep in mind, you're not just writing tangent squared theta because it's right here. You're writing it because this fraction right here and this fraction right here is telling you that when you divide sine and cosine, you get tan. Or in this case, dividing sine squared over cosine squared, you get tan. All right. You shouldn't be forcing this to be tan at the end. This value should give you tan. All right, example 6. We've got sine theta minus sine theta times cosine squared theta equals sine cubed theta. Now, if you want to pause this video and do it yourself, you're welcome to. I want to emphasize that if you just did this on your own and you got it, you might have a totally different way of doing this problem and getting it correct than the way that I do it. And that's perfectly fine as long as the way that you do it is legitimate math. All right, so what can we do here? I think I'd like to first start by rewriting cosine squared theta. So right here, rewriting this, I'm subtracting sine squared from both sides, and I see that cosine squared theta equals 1 minus sine squared theta. So I'm going to rewrite this as sine theta minus sine theta, and I've got to keep parentheses here. 1 minus sine squared theta equals sine cube theta. And you might as well assume that sine cube theta is just sine times sine times sine. All right, next thing we're going to do is do the distributive property. So this is going to be sine theta minus sine theta minus sine cubed theta. So sine times 1 is sine theta, or negative, because we've got the negative here. And then I'm doing a negative sine theta times a negative sine theta. And I kind of missed that, didn't I? It should be a positive because a negative times a negative is a positive. All right, next thing we do is we look at the left side of the equation and say, how can we simplify that? Well, you should realize that a sine theta minus a sine theta cancels out. And so we're just left with sine cubed theta equals sine cubed theta. And we've got a match, and we've done it. Okay, example 7 here. And example 7 is our last one. The left side is clearly more complicated than the right, and the first thing that kind of rings into my mind when I see this problem is rewriting cosecant and cotangent. Again, I kind of mentioned this. If it's ever written like that, it's usually useful to write it like that. That's not always the case, but that's a kind of a tip, I would say. So cosecant we can rewrite as 1 over sine theta. And cosine is just going to be cosine. And cotangent, we can see that here, is going to be 1 over tangent. Okay. I actually think we could probably do this a little bit faster. I mean, that's not a wrong step, but why don't we go ahead, instead of using that one, let's actually use this one. Cotangent is equal to cosine over sine. It's not wrong what I did before, but I'm feeling better about this idea. Okay. All right, let's go ahead and do this. What I'm going to do here is I'm going to multiply my fractions first. So that's going to give me 1 over sine theta is minus cosine squared theta, because here I'm doing cosine times cosine. And then I've got over sine theta. And I should be writing my sine theta straight down. Getting sloppy, Miss Sorensen. Come on. All right, now here we've got two fractions with a common denominator, which means we can combine them, and that's going to give me a 1 minus cosine squared theta over sine theta. We keep that common denominator, and we're trying to get it to be sine theta. What is 1 minus cosine squared theta? Hopefully you're getting the hang of this. If we solve that, if I subtract sine from both sides, if I subtract cosine squared from both sides, I get that sine squared theta equals 1 minus cosine squared theta. So I can replace this whole entire 1 minus cosine squared theta with sine squared. So this numerator is going to be rewritten, the whole thing, as sine squared theta over sine theta. Okay, we're going to continue over on the right here. And this might be a little tricky for you to see, and this might be an unnecessary step for some, but I can rewrite sine squared theta as sine theta times sine theta, and keep that divided by sine theta, equals, keep my right side as sine theta. So all I've done right here in this step is just rewrite sine squared theta as sine times sine. Now we get a cancel, and we're just left with sine theta, sine theta equal to sine theta. Because these two things canceled right here, and we're just left with this one right there. All right, y'all, that's how you prove trig identities. There's a ton of YouTube videos on these if you feel like you need to see more. I know that they're tricky. I trust that you can work on these, but just give yourself patience and you'll get through it. Thanks so much, everyone. Hope you have a fantastic day.